Hello again, this is the Pencrest High School AP Physics C video series. This is video 5C, Rotational, Kinetic Energy, and Work. So we already know that the kinetic energy is the energy of motion. Objects that are rotating also have kinetic energy. We are familiar with the standard linear kinetic energy formula, 1/2 mv squared. Knowing the rotational analogies for mass and velocity, we can see the rotational kinetic energy formula is 1/2 times I times omega squared. The rotational inertia, of course, is measured in kilogram meters squared, and omega in radians per second. When we multiply out the units, again, the radians go away because we want them to. We're left with kilogram meters squared per second squared, which is appropriate for joules. So this applies particularly to solid, rigid objects with physical dimensions that are rotating. So we have a standard formula that we used for a constant force doing work and applying or adding or taking energy away from a system in a in a linear sense. When we consider the rotational analogy, the analogy is not as neat as some of the others are. On the left, we have the work done by an applied force is Fd cosine theta, and on the right, we have the work done by a torque is torque times theta. We need to emphasize the difference in theta for each of these expressions. For linear work done, that theta refers to the angle between the force and the linear displacement. In the rotational case, theta refers to the angular displacement of the rotating object. So they are very different thetas, completely unrelated. So the units, of course, for torque are Newton meters. So they're already set up to provide units of energy. The radians associated with theta on the rotational side go away because we need them to. So you can think of it this way: if you apply a torque that makes an object rotate through some angular displacement theta, the amount of work done on the object, and assuming it starts from rest, the change in its kinetic energy would be equal to the torque, the net torque times theta. Now, the types of problems that we're going to see frequently that deal with work and energy in a rotational sense, we have this rod of length L and mass M. It's got a hinge on the left side, and the rod is released from rest in a horizontal position. It swings clockwise, and we want to know what its angular velocity is when it moves through some angular displacement. So we can consider torque equations in Newton's second law at any one particular position, but we cannot use rotational kinematics because the angular acceleration is not constant. As this thing swings through an angular displacement, the value for the torque changes, and therefore the value of alpha changes, and therefore we can't use kinematics. So we might be asked what the initial angular acceleration of the rod is immediately after it's released. We do need to use the parallel axis theorem to find the rotational inertia about the axis of rotation, which is over here at the end of the rod. If we look at sigma torque equals I times alpha, this here is my torque term. The mg is in the middle of the rod, pointing straight down. We can ignore the sine theta term. In this case, L over 2 is the distance from the rotation axis to where that weight mg is applied, which, because it's a uniform homogeneous rod, is in the middle. So there's my torque term, L over 2 times mg. We left out the sine 90. On the right, we have the rotational inertia that comes about by applying the parallel axis theorem. So what we have is 1/12 ml squared, which is a rod about an axis through its center of mass, plus mh squared. H in this case is L over 2. We square, we get L squared over 4. When we add those terms together, we get 1/3 ml squared. So there's the I term, and there's my alpha. I'm going to rearrange it, cancel out an m on both sides, cancel out one of the L's, and I get a fairly simple expression in terms of G and L. Now, going back to this thing swinging vertically, we're going to need to use conservation of energy to figure out the angular velocity as it passes through the vertical position. So the concept of gravitational potential energy being converted into kinetic energy is not new, but in this case the kinetic energy is rotational. So the key to problems of this type is that we need to know how far the center of mass of the object has fallen when the rod is vertical. So when we look at the work and kinetic energy principle, mg delta H equals delta K. The mg delta H is the work done by gravity, or the change in the gravitational potential energy. That delta H, once again, is the difference in the vertical position of the center of mass at the beginning of the problem and at the end of the problem. So think of it in terms of point A and point B. Point A is when the rod is released horizontally, and point B is when it has swung through 90 degrees and now it's vertical. So if we consider that the center of mass of the rod is in the middle, so it's at a distance L over 2, when the rod swings vertically, the center of mass will have dropped or fallen a vertical distance equal to L over 2. That's the delta H for the purposes of the work done. Okay, fairly straightforward when we have a single swinging rod like this one, but if you have a composite object, then we need to figure out where the center of mass is located, and at the beginning, and where it's located at the end, so that we can find that delta H term accurately. Also, we want to be careful about the mgh term, because the m needs to be the mass of the entire object. If it's a composite object, we may need to add a number of terms. So in this case on the left, here's my mg delta H term. L over 2 is the change in height when the rod swings vertically. And then on the right, 1/2 I omega squared. We clean up the expressions. We can eliminate one of the L's from each side. We can cross out the M's. And we get a fairly simple expression for omega in terms of G and L. Once again, the radians will appear because we want them to. You'll notice on the right, square 3g over L, the meters from meters per second squared over meters cancel, and we get per second squared under the radical sign. So the units are per second, and we then insert the radians because we need them to. Okay? So that's the key. What you want to remember is that whenever you have something swinging vertically, you need to apply conservation of energy, because you cannot use standard rotational kinematics. The angular acceleration is not constant, so it will not work. Okay, next up is angular momentum and its conservation. Until then, enjoy, and I'll see you again soon.